Hello, and welcome to this Vivado quick take tutorial focusing on using floor planning to increase design performance. We'll start off the agenda by talking about the various use models for floor planning. The most traditional use model for floor planning is to contain a specific section or module of logic for better performance. You can create an area of the device to contain that logic and to prevent it from spreading all over the device and lengthening delay times. Another use model is to lock specific logic in place to ensure consistency for subsequent runs. As an example, if I get good results in my place and route run, I can lock the block RAMs and DSPs or whatever other logic into place and create placement constraints for those so that they are locked in subsequent runs, which can help ensure consistency in those runs. Another use model is to use floor planning as a partitioning means for SSI devices. These stacked silicon interconnect devices actually have multiple silicon dies that have to be partitioned internally by the tools. You can floor plan your design to help that partitioning effort and to direct specific pieces of logic into the various SSI regions. And finally, another use model for floor planning is for partial reconfiguration and hierarchical design. These solutions often require floor planning to isolate the reconfigurable logic from the rest of the design. Various parameters are put on the floor plan region to ensure that no logic or routing from the outside encroaches in that space. This is covered in detail in the partial reconfiguration quick take tutorials and will not be covered in this one. So one of the big questions designers face is whether to use floor planning and how. We're going to start off the demonstration today by analyzing some flat implementation results that do not meet timing. We'll show you how you can use some of the design analysis techniques and features in Vivado to identify potential areas for floor planning. We'll show you how creating a dummy floor plan can help you analyze the data flow through the design, along with the resource requirements for the various logic modules. We'll then show you how you can analyze the flat placement to understand where and how you might want to floor plan your design. And then we'll look at timing issues. Where in the design are you struggling to meet timing, and where might floor planning help? We'll walk through the process of creating physical blocks or P blocks. These are the rectangles that are used to contain the logic for floor planning. We'll show you how you can use the P block properties to ensure that the size and shape of your P block can accommodate the logic you've assigned to it. There's a set of design rule checks that can be run to ensure your P block is integrity and is feasible for implementation. And often floor plan requires iterations on size, content, and location to meet timing. But once you've got a floor plan that works, it can be used to ensure consistency in subsequent runs or design modifications. We'll then finish up by showing you how you can lock specific logic modules or logic instances in place to ensure consistency in subsequent runs. To start, I'm going to invoke a Vivado design that does not meet timing. Let's start off with this simplistic example design. Notice from the timing report that there are several paths that do not meet timing. I can select each path and visibly see where they are in the device. Notice in the timing report you can see the from and the to, which is basically the source and the destination for that path. And in this case, all of these paths originate in this USB engine 0 module and end in the same module. I can select all of the paths listed, and notice you can see all of the placement for these particular modules are in the lower part of the device. So physically we can see where the timing problems exist, but what about logically? Let's have a closer look at these paths. I can invoke the schematic, and the schematic is created for me that shows all of the logic objects that are contained in each of the selected paths. One helpful hint is to try to find the smallest level of logic hierarchy that can contain all of the failing paths. It's more desirable to floor plan a smaller area as it can have a bigger effect. The larger the floor plan area, the more room the logic has to move around and affect timing. So here you can see that this USB engine 0 is the module that contains all of the failing timing paths. And here you can almost see that floor planning is heavily dependent on good RTL hierarchy design practices. By isolating clocks and critical logic module functions really pays off greatly if you're going to attempt to floor plan the design. Floor planning logic modules that have a high number of interface signals or that are connected to buses that may travel all over the design are sometimes very difficult to floor plan. So now that we've determined that all of our troublesome logic is inside the USB 0, it makes it a good candidate for floor planning. Notice as well there's also a USB engine 1 in the design. So these are two identical modules in the design, so for safety's sake we'll probably want to floor plan them both. Another logic analysis feature at your disposal is the hierarchy view. Notice when I use the show hierarchy command, I get a graphical representation of the logic hierarchy in the design. The rectangles represent the various logic modules at different levels of the design. They're drawn with relative sizes based on LUT count. So here you can see that the USB 0 and USB 1 logic modules make up quite a bit of the design. So the hierarchy and schematic views are excellent tools for you to examine your logical design. Sometimes it's not always apparent why a particular path is failing timing. Within Vivado, there are several ways that you can have a closer examination of specific paths. For example, I can turn on the routing resources in the device view to look at the actual routes that a particular path is taking. Sometimes due to logic or routing congestion, routes can tend to meander, which can affect timing. You can find out a lot more specifics about paths by selecting them and looking at the path properties. Notice the source and destination clock logic is described, as well as each of the loads on this particular path. All of the delays and the physical information about the paths are displayed in this view. So it's a good place for a detailed examination of any specific path. Vivado has another useful placement analysis tool at your disposal, and that's called Highlight. You can highlight all of the leaf cells for any placed logic module to see where the placer put them in the design. In this example, we'll highlight the USB 0 and USB 1 modules with different colors. Notice you can see where the placer put them, the USB 0 here on the bottom and the USB 1 up on top, so you can clearly see where you'd want to physically floor plan these logic modules in relation to the rest of the design. I'll now highlight all of the logic modules in the design using the Cycle Colors option to paint them all different colors. Notice this orange module that's spread all over the device, this NGT engine. This is probably not a good candidate for floor planning simply because the placer felt that it had to spread this module all over to connect the various parts of the design. If we isolated that in a particular area, it may negatively impact timing. You can use this placement analysis technique to help determine what to floor plan and where. So now that we've analyzed our design and determined which logic modules we wish to floor plan, let's go ahead and do that. Since we are defining physical constraints that will be passed to implementation, I'm going to choose to open up the synthesized design to assign those constraints. I could do it in the implemented design as well, but floor planning in there is a little cumbersome in that it's a little confusing to work with the place database that has all the placement constraints for the logic after implementation. It's much easier in the synthesized design. So I'll go ahead and select the USB engine module here in the logic hierarchy and use the draw pblock command to create a rectangle to contain that logic. Notice that I'm prompted for which types of logic I'd like to contain in this pblock. By default, we select all of the logic types that are inside the rectangle, but you could turn one off, for example DSP, and have all the DSP modules float outside of that rectangle if desired. So I'll elect to contain all of the logic, and the pblock rectangle is complete. To help us determine where to place the pblock, I'm going to turn on the display for I/O nets. And notice now you can see all the connectivity coming from the I/Os into the center of the pblock. Notice in the pblock properties view, the statistics tab shows the resource estimates for the various types of logic inside the pblock rectangle. The ones shown in red mean that I do not have the rectangle big enough to accommodate these types of resources, so I'll have to grow the rectangle. Notice I can just grab the edges and stretch it, and the statistics tab updates automatically. Or I can use the set pblock size command to draw another rectangle entirely. In this case, notice I've drawn a rectangle to encompass the clock region in the device, and I'm prompted to whether I want the range to be set as a clock region, which is also an option for pblocks. I'll do that. And notice I still don't have enough resources in there for all of the block rams and LUTs. So I'll make the rectangle bigger. And as you can see, I can adjust the size and look at the statistics until I get a reasonable utilization estimate that should implement. Now here again, you've got some options. If you make the rectangle too small, in other words, the utilization to be too high for LUTs, for example, say 90, 95%, you are limiting the number of logic sites available for outside logic to also use. As you'll see in the implemented results in a moment, that space is available for other logic, and it's actually desired so that you can help to connect to the outside world, outside this P block, and ensure timing is met. I'll now draw a similar P block for the USB 1 module, and I'll mimic what we did here for USB 0 since it is an identical module. And notice the connectivity to the I/O bank directly above the USB 0 I/O bank. I'll make this bottom P block just a little bit bigger to accommodate more slice logic, and I should be all set. Let's take a moment to review some of the other information provided in the P block properties window. As shown earlier, there are estimates for each type of resource inside of the P block rectangle. There's also a list of the number of carry chains and the largest carry chain. One of the common mistakes in floor planning is you don't create the rectangle tall enough to accommodate the tallest carry chain. This forces the placer to either fail or produce suboptimal results. There's a clock report detailing the clock names and number of clocked instances contained in the P block, as well as a utilization of the various clock regions report, and then an overall primitive count of all the different types of logic primitives assigned to this P block, and finally an interface signal count. Again, you want to choose modules that are somewhat isolated and do not have signals that connect all over the design. In this case, we can see we've got under 200 interface signals, which is highly desirable. I could get a closer look at those signals by clicking on the Connectivity tab, as you see here, and all the signal names are listed. The General tab allows me to set the P block ranges again, so I could exclude certain types of logic. And here I can also change the P block name. So now to ensure the integrity of the P blocks, I'm going to run DRC. And notice DRC has several types of different rule decks, with floor planning being one of them. Notice the different types of DRC rules for P blocks, including overutilization, P block carry chain height, overlapping P blocks, etc. And notice when I run the checks, I get no violations found. Let's go ahead for grins here and overlap these two P blocks. If I rerun DRC, I do get a warning telling me of that condition. This is not an illegal condition, but it's not necessarily desired either. If the intent is to have the two P blocks share that overlapping region and put logic in from either logic module, the Vivado placer really isn't optimized to do that. That's not to say it won't work and be successful, we just don't recommend it. So when possible, try to avoid overlapping P block situations. Now, having said that, what if one of the P blocks needs more resources and a rectangle doesn't suit our needs? You can create non-orthogonal shapes by using the Add P block rectangle command. Notice here I can create a different rectangle to add on to this rectangle to include that logic. And here you can see it's got a dotted line to visually show you that these two P blocks are connected. The resource estimations and the P block properties are updated to include both rectangles in the statistics. And I'll use undo to back out that rectangle change. So I'm now ready for implementation. The next step is to write these constraints into the constraint file that will be passed to implementation. Now I've got several options here. If I use the save command, it'll write these P block properties into my existing target XTC file. Or I can elect to create a new constraint set using the save constraints as command, which I'll do here. I'll call it constraint set 3. And notice this allows me to preserve my original constraints while experimenting with floor planning constraints through different constraint sets. I'll also elect to make it the active constraint set, which means it will be applied to any future implementation runs created. And I'll open up that new constraint file that was created, and notice it contains all of the constraints that were in my original constraint file, as well as at the bottom, these new P block constraints that we just created. Let's go ahead and launch implementation. So once implementation is completed, I'll open up the implemented design, and I'll do the same thing. I'll highlight the leaf cells that are under the USB 0 and USB 1 modules, and notice that they are placed within the P block rectangles along the left side of the device. Notice as well that there is other logic, this blue logic, that is also placed inside the P block rectangles. Again, as I mentioned earlier, that's desirable to allow a better connectivity to the outside world. There are special properties and parameters that you can put on your P-blocks to not allow other placement or routing to encroach in that space. These are primarily used for partial reconfiguration and not for floor planning for performance purposes. This design does meet timing now, but let's say for the sake of this demonstration it didn't. Sometimes creating the single rectangle is not enough. You'll still see timing violations for the logic that you've constrained inside the P-block. Let's imagine that we still had some failing timing paths that were inside this DMA module underneath the USB. We could create an additional P-block inside the original P-block to further constrain that logic. This is called a nested P-block. And notice the P-block here is completely inside of the other rectangle. All of the utilization estimates from the top level rectangle will consider and include the logic in the lower rectangle. We recommend that you use nested P-blocks sparingly and only when absolutely necessary. We also recommend that you do not go more than one level deep. In other words, only have one level of nested P-blocks. The Vivado placer is in no way tuned to support multiple levels of nested P-blocks. I want to take this opportunity to explain another nuance of using P-blocks. Notice the rectangles inside of the rectangles. Those are the logic instances that have been assigned to this P-block. In the first example, we just took one logic module and sent it to the P-block. But in reality, any logic in the design, regardless of whether it's in the same module or not, can be assigned to a common P-block. There are a few ways to do that, but the easiest way is to simply drag the logic from the netlist view into the rectangle as you see here. I did drag it into a nested area, so notice I get the choice of which P-block I want to assign the logic to. I'll choose the smaller one, and notice now you'll see two rectangles inside of that smaller P-block rectangle. These are the instances that are assigned, and they're displayed in relative sizes based on LUT count. Again, I want to make this point clear. Any logic in the design, whether it be a logic module or a leaf cell instance, can be assigned into a common P-block. This is helpful when you've got timing paths that are failing across multiple logic modules. Each of them can be assigned into a common P-block. I'll go ahead and back out these changes. And finally, I wanted to show you one more analysis capability that you can use P-blocks to achieve. Vivado does have some automatic P-block creation and placement routines that can help you with this top-level floor plan. There's also a physical constraints view that displays the various P-blocks created, and any nested P-blocks would show as hierarchy here. I'll quickly create P-blocks for each top-level module. You can create a top-level floor plan with small P-blocks for each of the top-level modules. What this will do is give you a good understanding of the logic flow through the design. Notice these thick colored lines. These are called net bundles, and they will increase in thickness and in color depending on how many signals are going between the various P-blocks. So you can see you can create a dummy top-level floor plan to visualize the data flow through the design through the various P-blocks. You can also look at the P-block properties to get a sense of the resources required for each of these top-level modules to help you make floor planning decisions. Now, we don't recommend that you create a P-block for all of the top-level modules because that will be pretty restrictive for the placer. The approach we recommend for floor planning is to only floor plan what's absolutely necessary and keep your floor plan at a minimum. Let the placer do its job. These are called constraints for a reason. They do constrain the placer, and too much floor planning can negatively impact timing results. Now I'm going to open up a stacked silicon interconnect design to show you how you can use floor planning to partition your design. These devices have separate pieces of silicon called silicon logic regions, and in this case you can see 4 of them. What I've done here is created a P-block for each silicon logic region, or SLR, and assign the logic that I want to each one of them. Vivado does have an auto-partitioning tool to automatically partition the design, but doing it this way gives you more user control over how the design is partitioned. And from here, each SLR can then be floor planned even further if you need that for performance reasons. So again, this is another useful way to use floor planning to achieve optimal performance. And lastly, I want to show you how you can lock individual logic objects to ensure consistency between runs. I'll now open up an implemented design to demonstrate that. Sometimes if you've got a design that's really packed or struggling to meet timing, achieving consistent run results can be problematic. One way to help ensure consistency is to lock specific logic or logic modules in place. In this example, I'll use the select leaf cell command to select all of the logic objects that are contained in the USB engine 0, and then use the fix cells command to lock them in place. Notice that after I use the fixed command, the logic appears in a different color, indicating that it has been fixed or locked in place. Now, we don't recommend locking large logic objects like this in place. The time spent to process the constraint files with all these locks in place can be excessive. We do recommend floor planning for larger modules like this. But there are instances where you can lock specific logic types, such as block RAMs and DSBs in place, and the next run would use that as a seed to ensure consistency. The easiest way to do that is to use the find command and to search for all of the primitive types of type BRAM and type DSB, as you see I've done here. The find command is quite extensive in that you can use a lot of different expressions and conditions and name filters to search for the types of objects you wish to find. I'm then presented with a find results table listing all of the logic objects that met my search criteria. I'll select them all here and again use the fix cells command to lock them in place. And then the last step is to write these constraints into my target XTC file for use in the next run. And again, if I use the save constraints command, it'll write these constraints into my current target constraint file. Or in this case, I'll elect to create another constraint set with these constraints. And notice when I open up that constraint file, I see all my original constraints that were in the design, as well as all of these lock constraints to lock the BRAMs and DSBs in place. And again, this is another method of floor planning to help you improve consistency in your results from run to run. So in summary, Vivado has many features to analyze your implementation results for potential floor planning. You've got the timing results view where you can highlight specific timing paths or groups of timing paths. You've got the schematic and hierarchy views for analyzing the logic hierarchy. The find command can be used to search for specific types of logic. And you can highlight the placement and connectivity of various logic modules or timing paths throughout the design. You can also create a top-level floor plan to help you visualize the data flow through the design and the resource requirements for the various logic modules. Logic can be contained in regions called P-blocks to improve performance. Vivado has a lot of different capabilities here, including the draw P-blocks command, set P-block size, and we provide P-blocks utilization statistics to help you create the optimal size P-blocks. You can partition your stacked silicon interconnect designs with P-blocks to help improve performance. And finally, individual logic or logic modules can be locked in place for subsequent runs. And finally, we'll close with some P-block suggestions. Floor plan can definitely improve performance and consistency between results. But only floor plan what is necessary and avoid over floor planning the design. Use your design knowledge coupled with the Vivado features to create the floor plan. And good floor planning always starts with well-planned RTL hierarchy. Isolate the clocks, limit external interconnect, and register the inputs and outputs if desired for better performance. And finally, as mentioned, floor planning is an iterative process. Be patient with it because once you get a floor plan that works, it will improve consistency and performance in subsequent runs. Thank you very much for your time.